Good morning. Here we are once again at the physics video lecture. Physics 105A video lecture 19. Let's begin. The topic of the day is driven oscillations. And we had already gotten quite a ways through there. I'll remind us what we ended up with was the resonance catastrophe of the driven oscillation. And we had no damping in our system, so let's go ahead and remind ourselves here. Driven oscillations. Remember, the differential equation was mass times acceleration. Okay, we've got the restoring force, the Hooke's law restoring force, plus f of t. Of course, then we turned that into this differential equation by dividing by m, omega naught squared x, f of t over m, and we found an interesting way to solve this using complex numbers. But what we did after that was, so I like to number things, right? We then looked at driving it not just with any force. By the way, our formulas have allowed us to drive it with anything whatsoever, but we then drove it with the cosine omega naught squared x equals some constant f naught over m cosine omega t. Now, omega and omega naught are not the same thing, right? The omega 0 is root k over m. This one, on the other hand, we can imagine dialing in. We can dial in the frequency that we want, and we find that when we drive this system with the natural frequency omega naught, the solution grows linearly in time. And that's actually the catastrophe, so-called. So if omega approaches omega naught, then we end up with x of t proportional to time. Of course, it's still oscillating, and we could say we had something like this. And since it's growing linearly, I can just draw a linear envelope, and our oscillations are growing like that. So that was our result last time, and I put some of the details of the calculation on your homework, but I actually showed you rigorously where this time proportionality came from. So actually, if resonance, if oscillations keep growing in magnitude, the solution becomes unphysical. Okay? And in fact, if you remember that this differential equation came from looking for a local minimum of potential energy, linear force law, then the amplitude actually grows out of bounds of what justified this expression here. Be that as it may. So that would be the resonance catastrophe. And what we're going to do next, these were undamped. And what we're going to do next is look at the differential equation that we'd already seen before with the damped oscillations. So now we're talking damped driven oscillations. Damped and driven oscillations. So we've seen this before. What we would have would be that friction force proportional to x dot over here, and when we bring it into there, we would have the following. So x double dot plus 2 gamma x dot plus omega naught squared x is equal to f of t over m. Now we've studied this left side of this equation when the driving force is equal to 0, okay? And we know the answer. So I had mentioned before, you have the solution to the homogeneous equation, which is when the force is 0, and the solution to the inhomogeneous equation is when the force is there, okay? And that's what we have to find this time. But first let me write that x of t, the solution, is equal to the solution to the homogeneous equation plus solution to the inhomogeneous equation. Because if you take this solution here, both of these parts, into this differential equation, for the homogeneous equation, these operations equal 0. Okay, so you're done. So we need one particular solution, one inhomogeneous solution. Then when we apply this operation to it, the right side is equal to f of t over m. Not only that, we also know what this thing is here. So this is a cos root omega naught squared plus gamma squared minus t plus some alpha and this we don't know yet. Oh, actually, not so fast. Got room over here. E to the minus gamma t. That was going to be my whole point here. Okay. Because the solution to the homogeneous equation, which has this to us now well-known form, decays in time to 0. So we say that it is transient. Okay, so this is a transient solution. And although it's part of the general solution, we're just going to ignore it because we already know what's happening here. And what we have to do now is find the solution to the inhomogeneous equation. So transient means goes to 0 as t goes to infinity. Okay. So now our task is to solve this equation. And we're going to, in this case, you know, we can actually generalize our technique from before with complex numbers, but we're not going to. We're going to do a standard operation to find the solution to the inhomogeneous equation. And well, we'll see. What's going to be interesting about it is the behavior of the amplitude. Here we thought that's just a number and we're done. Here it's going to get interesting. So let's go. What we're going to do for our trial solution, or solution of this equation here, we're going to let f of t be equal to f0 cos omega t, as we did before. And this time, we're going to go ahead and plug in the complex version. So, complex F, I'm not going to give it a new letter, F naught e to the I omega t, and then we're going to be able to take the real part when we're done, okay? Same thing holds true that we've said all along about taking the real part after we do all of our operations. So we're going to take this into here, and our x now, which is also complex, I'm not going to call it z, I'm just going to call it x. We'll take the real part later. Is going to be a e to the I omega t. Yeah, maybe we'll go ahead and call it z. Okay. So this time a is complex, but these two omegas are the same. What we're saying is, and we're going to prove it in a moment, but what we're claiming is that when you drive a system like this, after the transient dies away, the system is now oscillating with the driving frequency. Okay. So that's the assumption that's being made here. It'll be justified as we go through here. I'll put this as a note. As t goes to infinity, the system will be oscillating with the driving frequency. Okay, oscillates with the driving frequency. This is all complex now. Omega is real. A is complex. That's our complex exponential. Okay, let's set this up and see what happens. We're using the differential equation in the blue box. And I can actually just point at it. The left side of our equation, we have, well, let's go ahead and write it like this. We'll rewrite the differential equation. 2 gamma z dot omega naught squared z equals f naught over m e to the I omega t. Okay. So with this trial solution, we have a times, because a is going to be common to all of these. Well, let's put a afterwards. We have two derivatives, so I omega squared, 2 gamma, one derivative, I omega, plus omega naught squared. That's all being multiplied by a e to the I omega t. And we're saying that's equal to f naught over m e to the I omega t. Now this time we're not letting this thing go to 0, because remember, omega naught and omega are not the same thing. So yeah, we're going to take this at face value. That's what it means to solve this differential equation. But what we can do is get rid of this thing here, and what we see now, remember, this omega is the driving frequency, so it's the machines, whatever's driving our system. Gamma, these are all constants that are given. So the unknown is the amplitude. So what we're going to do is solve for the amplitude. And this contains all of the interesting physics, really, or most all of the physics that we're looking for. So what is the amplitude? A is equal to f naught over m, and then we're just dividing by this thing here. So minus omega squared plus omega naught squared plus I times 2 gamma omega. So the amplitude is complex. And what we have to do is turn it into a real amplitude because we want the real part of this whole thing, right? So right now, z a to the I omega t, we know that we would have a cosine omega t here, that's fine. So we need the real part of the amplitude. Okay. So I'll just put here next. Find the real part of the amplitude. Good. So the way we do that is we multiply top and bottom by the complex conjugate of this expression in the denominator. So let's just keep going with a, f naught over m. We have in the denominator minus omega squared plus omega naught squared plus I times 2 gamma omega. And then we're going to multiply by the complex conjugate, so minus I 2 gamma omega. And we do that in the numerator as well. So there's a 1 minus omega squared plus omega naught squared minus I 2 gamma omega. So far we've just multiplied by 1. F naught over m. So what's our denominator? Our denominator is this expression squared plus that squared there. Cross terms go away, so it's omega naught squared minus omega squared quantity squared plus 4 gamma squared omega squared. And the numerator still has these two parts. Let's go ahead and write minus omega squared plus omega naught squared plus I times 2 gamma omega. So yeah, there's the amplitude, and we can now see the real part. It'll be this f naught over m, real part divided by that. Okay. So far so good. We want to do a second thing though. So we have that there, that's fine. So what we want to do next is write A equals the magnitude of A times e to the I b. Okay. I want to write it as magnitude e to the I times p. Remember, that's a standard way to write a complex number. It's always just as simple as being here in the complex plane, having a complex number, magnitude e to the I phi. Okay. So that's our next task. So what is the magnitude of this number right here? Okay. Actually, magnitude and phase. So actually, how about we look at the phase first, okay? Because the phase would just be the inverse tangent of the imaginary part divided by the real part. So we could say that tangent of phi is equal to 2 gamma omega divided by omega naught squared minus omega squared. far so good. What about the magnitude of the amplitude there? So we can also read off, because numerator and denominator have these same constituents. This is squared as to what we have up there. So we immediately, well, the F naught over M doesn't change. We have 1 over root omega naught squared minus omega squared. Quantity squared plus 4 gamma squared omega squared. And there you have it. See, if you take the magnitude of, we gotta put that in red. So my square red, my red bracket there, see, I'm going to have what's in the numerator squared in the denominator if I take the magnitudes of numerator and denominator. And so then I cancel the one from the other, and I'm left with this right there. So we're ready to collect our result. Now we can take the real part of everything. Is going to be the real part of A e to the I omega t. It's going to be the real part of A e to the I omega t plus I phi, okay, which means we're going to have this amplitude F naught over M 1 over root naught squared minus omega squared 4 gamma squared omega squared, and then this cosine of omega t plus phi. Okay, let's admire this for a moment. There's some interesting physics in this phase shift that we can also get to. But other than that, this is just oscillating with the frequency that we're driving it with. And all of the interest is apparently going to be in this expression right here. So the behavior of the amplitude in terms of these quantities is what we're going to be studying next. Okay. We assume that the oscillation frequency would be the same as the driving frequency, and it clearly was. Okay. But there is a phase shift involved with comparing the two, the driving and the response frequency, and then there is this whole interesting expression for the amplitude. Okay. Is there anything else to say about that before we erase this board here? good to me. Make sure you see the step that I took to get from here to here. Okay. The magnitude of the numerator would be the square root of these things squared. The denominator has them without the square root, so I cancel the square root against the square root squared, and I'm left with a square root. Okay, good. So let's analyze this thing here. Go right directly under here. In fact, I'm going to do a graph of this expression right here. Okay. In fact, I'll do it directly underneath. That's not bad. And we're looking at this amplitude as a function of omega. And there's some limiting cases. The first limiting case, of course, we have to go back to the undamped quantity. So let's just kill omega squared here. And what do we have? And clearly we can go ahead and look at omega naught. Do some dots right there. In the limit, as gamma squared is equal to 0, we've got something that's going to diverge when omega goes to omega naught. So we would have something diverging like that. In fact, you see that would be our resonance catastrophe. And remember, this is the transient, so this isn't telling us how it starts resonating. This tells us the final amplitude, and if gamma is equal to 0, we can have an unbounded amplitude there. So if gamma is not 0, we expect to have a maximum here at omega sub 0. Okay. So let's go ahead and do that. So I'll just put a couple of notes here. First one, if gamma equals 0, then amplitude diverges at omega equals omega 0, clearly. So the second case, gamma is not equal to 0. Let's do d amplitude d omega. Let's just take the derivative. Aside from all this stuff here, f naught over m. This is minus 1/2 power, so we have minus 1/2 this thing to the 3/2. Okay, so the third, but we're trying to find where it vanishes. So we take the derivative inside there. We have 2 omega naught squared minus omega squared times negative 2 omega for the inner derivative plus 4 gamma squared times 2 omega. Okay. Gonna run out of room right there, but yeah, I'm just taking the derivative of this thing. That's the inner derivative. When it vanishes, we have 2 times 2, 4. And 4 times 2, 8. So what do we have here? We have 4 omega naught squared minus omega squared plus 4 omega times 2 gamma squared is equal to 0. 4 omegas are gone, so we have omega squared equals minus 2 gamma squared. So in the limit as gamma goes to 0, we have, again, the peak right here. Okay, let me consult the clock. Okay, let's check this before we move on. Omega squared. Zero. 4 omega. Got a minus sign here. Omega squared minus omega naught squared. Gamma squared. Yeah. Okay. So we can see where the resonance is going to be at. And let's go ahead and draw this whole thing. That was fun. Let's go ahead and draw this. A little more carefully this time. So we have amplitude as a function of omega. When omega is equal to 0, we actually have A of omega equals 0. This actually has some significance. F naught over m, this is 0, this is 0, m omega naught squared. Because we've got square, okay, so is equal to F naught over m omega naught squared. And this is significant because omega equals 0 means we just have a constant driving force, which is what we've talked about before, and we've seen this before. M omega naught squared is k, F naught over k, the spring constant. So there's that finite value. And then if gamma is reasonably small, especially, then this thing can get very large, since we know it diverges in the limit. So it's going to go up here. Okay, have a peak, and then for very large omega, this omega to the 4th dominates everything else. Okay, for very large omega, this denominator just gets arbitrarily large, so the number gets arbitrarily small. So you have this behavior here, asymptotic to 0, and you've got your peak around omega naught. So now the way to look at this, I didn't bring the machine in, all-time demo, but you're driving this system with this frequency omega. If you start at really low frequencies, there's nothing going on. Okay, it's just displaced. And then as you increase the frequency, the amplitude increases. Again, in the limit of a vanishing damping, it would actually catastrophically grow up to infinity. Of course it doesn't. So it has a finite height, and then it peaks and decays back down again. Okay. So that's why we went through all of this, the interest here is, once again, imagining you can dial in this frequency and just increase it, and your system responds by having a very large amplitude at some resonant frequency, and then decaying out as frequency goes to infinity. Okay, that's where we're going to stop for today. So this is called Amplitude Resonance. Amplitude Resonance. And just always imagine that you're turning this frequency up and watching the system grow and grow in amplitude. And as you keep turning the frequency up, it peaks, goes down to 0. So this is where the major response is. And we already learned that when it comes to the energy absorbed by the system, it had to do with some, we don't have Fourier series, it had to do with the Fourier integral of the resonant frequency. So we'll see more of that later. Good, so we'll leave it now with amplitude resonance. The next section, we're going to express this energy, or we're going to investigate the energy of the oscillator, and then we'll get a similar curve called the energy resonance curve. But we'll do that next time. See you then.